Vectors in a plane. So, vectors look very much like a, I don't know, ray from geometry, if you remember those. A couple things about vectors. I wanted to separate the thought here. Scalar quantity. So a scalar quantity is anything that can be measured using real numbers. And they give examples like mass, length, volume, density, speed. These are all scalar quantities. It's really one thing. You're telling me one thing. Speed is miles per second, but you're still telling me one thing. Mass, you're telling me one thing going on there with it. So this is scalar. This is what you are used to when you are just describing some type of measurement. When we get into vectors, vectors are different. So while scalar quantity has one measurement, vector quantity is a quantity that's described by both a number and a direction, okay? And so that direction is very important. It changes how you treat this. So all of a sudden, instead of just telling me miles per hour, now we have 7 north horizontally to the north, or 9.26 meters per second east. And so all of a sudden we have a direction. One of the ways that we in the past have described direction is with positives and negatives, right? And so if you watch football, they'll say they gained 3 yards, they lost 3 yards. Well, they're actually telling me a vector there because they're actually giving me a measurement and a direction as well. And so when you can have the measurement with the direction, you no longer have just a scalar quantity, you now have a vector quantity. And so that is the difference between the two. So let's talk about a little bit of, all right. So we have some notation. The vector is notated PQ and it has what looks like a ray, but you'll notice it just has a half of the arrow there. All right. Half of the arrow, that is a vector. It has the length of PQ and the direction of the ray PQ. So we are now combining like a line segment and a ray is what we're doing. All right, because a ray is infinite. Yes, a ray starts at a point, goes on infinitely. It does not have a length, it has direction. A line segment has the length, but no direction, right? And so when you combine those, you get a ray. And so that's what they've done. They've taken the line segment with the ray, they've combined those two notations. So we have just half of that arrow at the top. It indicates a vector, all right? Because it has direction, order matters. It does not matter with a line segment how you list the points, right? Because from P to Q and Q to P for a line segment is the same thing. For a ray, it matters because you have a starting and an ending, or starting and a continuation point. For vectors, it also matters because you have a starting, which is called the tail. You have an ending, which is called the head. Okay, tail, head. You can think of it like a plane. The tail of the plane, the head of the plane, right? You can think of it that way. But it does matter which way you list it. From P to Q is one direction, from Q to P is a different direction. Therefore, it is a different vector because vectors we're going to deal with angles as well. So angular measure will matter if you are going one way or the other. So a little bit of things that have to do with these. Initial point, that is the tail. Initial point is the tail. Terminal point is the head. You'll notice that we have x1, y1, x2, y2. So this matters when we're talking about how we calculate some of these things. The distance here, well, we're just subtracting the two x's to get the horizontal distance, subtracting the two y's to get the vertical distance, which makes sense. And you can see from this that we're going to be using some right triangle stuff, right? Some trig, and this is how it's developed. This is how we develop all of those little, which you probably have done, like A, cosine of x, B, cosine of y, or whatever you've done in the past with some of your physics stuff. It comes from your right angle trigonometry. All right, terminology here. Component form. So let's talk about component form. They are broken down into the different components, horizontal and vertical components. And so you'll have a starting and an ending point like they have here. Given P and Q, express PQ, so from P to Q, in component form, and draw an equal vector V in standard position. Okay, so let's talk about what all of that means. We're going to break this down into components. And basically in standard position means from the origin, all right? So if we look at where this is located right now, we would just basically go to the point 4, 2. All right, so 4, 2, that's this point right here. And then the ending point would be 1, negative 2. So that's this guy right here. And this would be my vector. If I draw from my, always have to draw from my starting to my ending, right? And we need a direction. So we do have to do the arrow telling me the direction that that vector is going. All right. This being P and this being Q. All right. So that's easy enough. But now they're saying, okay, standard position means where would that lie on the coordinate plane if I started at the origin? So let's think back with trigonometry. Every angle of the same measurement is going to have the same trig functions, right? So any 30-degree angle is going to have the same sine. Sine is going to be 1/2. It does not matter where on the coordinate plane that 30-degree angle sits, right? It does not matter how long the legs of the 30-degree angle are. It will still have a ratio of opposite over hypotenuse of 1/2. Always for a 30-degree angle. And so it doesn't matter if we were moving this guy anywhere on the coordinate plane, it would not change anything that we calculate with him. It just makes our lives a little easier to do standard position from the origin. So now we have to figure out what that means. When you express it in component form, you put these two together. So I am going to take my ending and subtract my beginning, all right? So in this case, I am going to start with the x values, all right? And so I am going to say, with my x values, I'm going to figure out what my x value would be of my vector. So I would say my ending x value is 1, my beginning x value is 4, that gives me a negative 3. I'm going to do the same thing with the second piece of this, the y values. My ending y value is negative 2. My beginning y value is positive 2. Subtract that, I get negative 4. All right? So how do I express this guy? Well, I would say that PQ in standard position looks like this. You'll notice my notation changed. I no longer have parentheses. Parentheses represent a coordinate point, xy. These little arrowheads almost is what they look like here. These little brackets represent a vector. And what that means is starting from the origin, this tells me how to move to the ending point. So in this case, my origin will be my starting point, and negative 3, negative 4 will be my ending point right there. And so this is how I'm going to draw this vector in standard position. You'll see that it is identical. It is identical in slope. It is identical in length. It is identical in direction, okay? All I did was basically slide it to start at the origin. That is standard position for this guy, standard position. So you take your ending points, subtract your beginning points, and you get your standard position point, and you notate it with these little brackets, all right? So I no longer have to give the starting and ending point. I can give one vector notation in standard position, all right? All right, so magnitude and direction. This is given the vector in component form. So you'll notice at the top of these formulas, you have a little v with a little vector notation, and then you have your notation in standard form, okay? So if you have your two endpoints, you have to calculate standard form, or you have to use your distance formula, basically, is what you're doing. This is really just your distance formula. You've already subtracted the two, right? So think about your distance formula, x2 minus x1 quantity squared plus y2 minus y1 quantity squared, take the square root. If you have it in vector form, in standard form, you already have done your x2 minus x1. That's what we just did to get it in component form, right? Or in standard form. So the magnitude is literally the length. Magnitude is the length. If we're talking about a word problem, it's distance traveled. They traveled 300 miles in this direction. They gave you magnitude, okay? So magnitude is the length of the vector. That's where we get this formula, the square root of a squared plus b squared. That is strictly from your distance formula, all right? Your reference angle, notice the term reference angle. This is always going to give you an angle from 0 to 90 degrees, always. So your reference angle is going to be your inverse tangent, right? Tangent -1 on your calculator. We're finding angle of b over a. Why? Well, tangent is y over x, okay? So we just did the inverse tangent of y over x. That's what tangent always is in a right triangle, okay? So that's where we're finding our reference angle. The next piece of this is telling you what to do with that reference angle. How will you know what quadrant you're in? Well, they gave you your x and y. Your x and y tells you what quadrant you're in. Positive, positive, quadrant 1, right? Negative, positive, quadrant 2, negative, negative, quadrant 3, and so on. So your coordinates will tell you what quadrant you're in. If you're in quadrant 1, your reference angle is your angle because it's from 0 to 90. If you are in quadrant 2, you'll notice that you subtract from 180 because remember, it's the closest angle to your x-axis. So they have given you your reference angle to figure out your actual angle, subtract from 180. If you are in the third quadrant, you went past 180. So you take your reference angle and you add it to 180. If you are in the fourth quadrant, you are closest to your 360. So you're going to subtract from 360 to get there. All right, does everybody understand what they have just done? First quadrant, they gave it to you. Second quadrant, third, and fourth, you're going to have to calculate based on where you are. All right, so let's look at this next example. Finding the magnitude and the direction of a vector. They are taking the example 1 vector. All right, the example 1 vector. We already calculated it in component form. So in standard form, we already figured out that PQ standard form looks like this. Okay? And they will not always give you a picture. So we're looking at a picture, but you're not going to actually have a picture. You're just going to have the component form, or you're going to have the 2 pieces and you're going to find the vector standard form and do it from there. So if they want the magnitude, we're just going to plug that in. My magnitude of this vector. Couple things about the notation. Notice this up here. The vectors can be notated with a lowercase or the 2 letters that represent it, in this case PQ. So if I were to do magnitude here, I would do it like this. PQ, when you have 2 letters, you have to have your notation above it. When it is denoted with 1 lowercase, you don't need the little half arrow above it. Magnitude, though, represents, it looks like absolute value there. All right, we are talking about a distance, so it makes sense. All right, and so to calculate it, we're just going to do the calculation of -3 squared plus -4 squared. That is the square root of 25. That is going to be 5. All right, so my magnitude here is 5. That solved the first question. Direction is my angular movement in standard position. All right, so if you remember, standard position, even on the unit circle here, starts over here and goes counterclockwise, right? So when they say standard position, that's what they're talking about, the angular movement in standard position. And so to calculate that, we're going to say the inverse tangent of my -4 divided by my -3. When you do that in your calculators, first of all, we are talking about angles in degrees, not in radians, okay? So first make sure you're in degrees. You'll get a weird answer if you're in radians. In degrees, you'll get approximately 53.1 degrees. All right? That is not my movement. If I move 53.1 degrees, I would be up here, right? So I have to go back and say, what quadrant am I in? Well, -3, -4 puts me in this quadrant, which means I have to take that 53.1 and I have to add this 180 to it. All they did was give me this. They gave me the reference angle. So I have to add the 180 to it to get my actual final movement. So the movement here, the direction, is 233.1 degrees. That is the second part of this question. Easy enough? Mm-hmm. All right, let's do it. The sum of two vectors can be found by placing the tail of the second to the head of the first. The resultant vector from the tail of the first to the head of the second, when the vectors are expressed in component form, their sum is found by adding the corresponding components. They give a little, he was not a mathematician or a scientist, but he was the first to publish this concept. All right, so vector sum. We have two definitions here. Vector sum, or the resultant vector, they mean the same thing, of two different vectors, vector u and vector v. The vector sum, or the resultant, if they ask for the resultant vector, they actually just want you to add them. All right, you're adding your x values, you're adding your y values. You can also do scalar. Hopefully the word scalar means something to you. In matrices, scalar is just the guy you multiply on the outside. In geometry, scale products, well, that's if you take a similar figure, whatever you multiply everything by the scale factor. So just in every other definition that you've ever used scalar product, you literally are just multiplying each piece by something, like distribution. Think of it like distribution. Scalar is always done like distribution. It goes to each piece of whatever you happen to be talking about. In this case, we're talking about a vector. Vector subtraction is the same as any other definition of subtraction, adding the opposite, okay? So adding the opposite is subtraction. So you can, if you are adding them or subtracting them, you do exactly what you would do when you are doing matrices. The corresponding pieces add or subtract. That's all you do. And so you can put those two together and do some calculations. You can do some, it is as simple as it looks. They want us to do the sum of u and v. Well, if I'm going to do the sum of u and v, I'm going to add the pieces. Negative 2 plus 6, that's going to give me a 4. 1 plus 3, that's going to give me a 4. It is that simple, all right? For the next one, they have 1/3 v minus 2u. All right, so let's actually write it the right way. There we go. Distribute and solve. So we're going to get 6 times 1/3. That's much prettier. All right. And again, you are adding the opposite. They changed it. You don't have to change it to adding the opposite. Just make sure you pay attention to your positives and negatives. So 2 minus a negative 4. 1 minus 2. That is my resultant for that. All right, that is my resultant. Tail and head. So we're going to do tail of the first to the head of the second is what you're doing here. All right, any vector u with a magnitude of 1 is a unit vector. That makes sense, right? So think about everything else we've done. We've done things in units. So if you say 53 miles per hour, that's actually a unit rate, right? Per 1 hour. That's what you're telling me is a unit rate. And so vectors also have unit vectors. The way you find a unit vector that is in the direction of the vector that you have is using its magnitude. So you take the vector and you divide by its magnitude. And then you will have its unit vector. So the first thing you have to do is find the magnitude. You find the magnitude with your formula, right? So we're going to take, if we want to find the magnitude of this vector, we're going to do the square root of 3 squared plus negative 5 squared. We're going to get the square root of 34. That is not reducible, right? It's 2 times 17. They're both primes. Okay, so we can't simplify that. We're not going to put it as a decimal. We're going to leave it as a radical, all right? We're going to get exact. And then we want to divide. Well, division, we haven't talked about division, but division is just multiplying by the inverse, so scalar multiplication. So if I were to take 1 over the square root of 34 and multiply it by that vector, that's the same thing as dividing. And so my unit vector here is going to be 3 over the square root of 34, right? But if we rationalize that, it would look like this. And then negative 5 over the square root of 34. But again, if we rationalize it, it looks like this. All right. And so that is my unit vector. Now this is saying that all the unit vectors should have a magnitude of 1. So you can actually check this by checking its magnitude. You can check the magnitude of this. This is the unit vector. You are actually done. That is your answer if you're asking for the unit vector, but you can check it by checking this magnitude. And you can say, I would actually check the magnitude this way, 3 over the square root of 34. I would actually square it that way. A squared plus b squared square root. That should have that length should be 1. And so if you do that, you get 9 over 34 plus 25 over 34, which gives you 34 over 34, which gives you 1. The square root of 1 is 1. All right. And so if you have done your unit vector correctly, your length should be 1. Your magnitude of that should be 1. Okay. So if they want unit vector, you're going to find the magnitude. You're going to divide your original vector by its own magnitude, and that is its unit vector. You can check it by making sure the magnitude of the vector that you came up with was 1, because your unit vector should have a magnitude of 1. All right. So standard unit vectors, we've talked about standard position. That's when we just have the x and the y with the brackets. You have standard unit vectors. So we have, and it's labeled I, but you'll notice this is going to be your standard unit vector for your x position. This is going to be your standard unit vector for your y position. All right. So in standard position, you're just going to have your brackets with your x and y. You can actually write it in a component form. So standard form is just going to be the 2 brackets. Component form is going to represent what you are multiplying each of those by to get the standard form pretty much. So when you have your x and y, if you just put an ij next to it, it represents those unit vectors. And it's just 2 different forms of the same thing. Think of it as standard form of a linear equation, ax plus by equals c, versus slope-intercept form, y equals mx plus b. Those are 2 forms of the same equation, all right? So these are just 2 different forms of the same vector. Standard form is just going to be the bracket with the x and y. Component form is going to include your ij, and ij just represents those unit vectors, all right? It's just another way to write it. So if they were to say, write this vector PQ as a linear combination of your standard unit vectors, they want it in that combination form, then you are just going to figure out your standard form and spread it out with I and j. All right. So I'm going to figure out my standard form using my subtraction. Remember to figure out my standard form here, my vector form, then I am going to just subtract these. 9 minus a negative 2 is going to give me 11. Negative 7 minus 5 is going to give me a negative 12, all right? That's what we've been using. If they want it as a combination of standard unit vectors, you're just going to take that out and you're going to say, well, it's the same thing if I were to take the 11 and multiply it by the unit vector for the x, 1, 0. And if I were to take the 12, I did subtraction only because it's a negative 12, and multiply it by the standard unit vector for the y position, 0, 1. Okay? So that's just a different way to write this guy right here. Those are 2 ways to write the same thing. That's what they're wanting when they ask for something like that.